Okay, page 25 in your package. We're going to continue looking at stretches and reflections. And again, if I had $1 every time I've said this the last, I don't know how many years, that you have to memorize this stuff, I'd be rich. I wouldn't have to work anymore. But you have to memorize this stuff. You're going to be tested on it many, many times on the diploma exam. So you have to remember what all these parameters do. We've seen that H shifts the graph left and right. H is hooked directly onto the x with a plus or a minus. Whatever happens to the x happens to the x minus h, whether it's squared, square root, absolute value, doesn't matter. Whatever happens to the x happens to the x minus h. And the value of the h is always the opposite of what it appears to be because our general equation has x minus h there. When h is positive, the graph goes to the right, but the equation stays x minus. When the value of h is negative, the graph goes to the left, but the equation changes to x plus. Okay, so got to remember that. K shifts the graph up and down. Normally we get y by itself, so the k is at the end, and whatever the value of k is, that tells you how far up or down it goes. When k is positive, it goes up. When k is negative, it goes down. Then yesterday we saw that a does two different things. If a is negative, it reflects it over the x-axis, but it also causes a vertical stretch. And that vertical stretch is the absolute value of a. And because it's stretching vertically, it's the y values that change. You multiply all the y values by the a value to get the new y values. And then we saw that b causes a horizontal stretch, but the stretch factor is the reciprocal of b. The horizontal stretch factor is by a factor of 1 over the absolute value of b. And then when b is negative, the graph reflects over the y-axis. So you have to memorize all this stuff. Okay, there's no two ways around it. So let's continue doing some more practice. The graph of f at x is given. Transform the graph of f at x to sketch the graph of g at x. It asks us to describe the transformation, state any invariant points, and also we're going to add the domain and range of the functions. And now as well, we're going to do the mapping notation. So for the first one, we're going to go g at x equaling twice f at x. You want to put your phone away, please? Thank you. So you have to look at that equation and see, because it's in front of f, that's our a value. And you have to remember what that does. It causes a vertical stretch by a factor of a. In this case, a vertical stretch by a factor of 2. So let's write that description right now before we even graph it. We're going to have a vertical stretch, and you have to state about what axis it's being stretched from. A vertical stretch about the x-axis by a factor of 2. Because in this case, a equals 2. And so that means that all the y values are multiplied by 2. If you're vertically stretching, verticals up and down, it's the y values that go up and down. The x values will not change, but the y values will be twice what they were before. So this starting point here with a y value of 4 will become a y value of 8. The x-intercepts are invariant because they are 0 units away from the y-axis. So that distance won't change because a y value of 0 times any stretch factor will stay 0. This point here with a y value of 2 will be stretched to a y value of 4. And this point here with a y value of 4 will be stretched to a y value of 8. So these are the key points that we will use to sketch the graph of g at x. So the x-intercepts again are invariant. The y-intercept changed. The original graph doesn't have arrows on it. It has a definite starting point and a definite ending point. So our new graph would have the same characteristics. So that's what g at x will look like after a vertical stretch by a factor of 2. Okay, so we've described the transformations. We have done it. Then we're going to state our invariant points. They are at the x-intercepts. Whoa. plus and minus 2 comma 0. So you can use that to write only once instead of both points separately. We also want to state the domain and the range. So remember, the domain are all the x values. And there's two different ways you can express domain and range. One of them being interval notation. That's the easiest way to do it. With interval notation, there are a couple key things. You have to make sure you use the right type of brackets. Square brackets means that the starting and ending values are also included. So in this case here, x goes from -6 to +6. Interval notation would look like that. The other part about interval notation you have to make sure that you do is it's always the smaller value first, followed by the larger value second. Any examples where you have going to infinity or negative infinity? In those cases, you have to use the round brackets. The round brackets means that the end values are not included, but in this case they are. Same thing with the range. The range is asking what values of y are part of this relation. You're going from a minimum of 0 up to a maximum of 8. And again, the square brackets are used because those n values are part of the range. And then the last part, the mapping notation, because we multiplied all the y values by 2, we would say that x comma y maps into x comma 2y. The mapping notation must have both of these components, the x comma y first, followed by an arrow with the new components. In the last couple diploma exams, there have been questions on the written response where this needed to be done. The nice thing about it too is this was true in January's exam as well as the previous one where mapping notation came up. There was a question in the multiple choice that showed a mapping notation for a function. So the format was there for a student. If they were kind of paying attention and reading, there was a question on the multiple choice where they had a mapping notation. The format was there. So you just had to follow the same format when you wrote it on the written response, which was what we have written down here. And that's something that they will do often. Something that is on the written response, there'll be something to do with that same concept in the machine scored, either the numerical response or the multiple choice. Okay, the second one. I think we did everything we were asked to do there. Yeah. So for the second one, we want to write g at x equaling 1/2 f at x. Again, where is that 1/2? It's in front of the f, which means that's an a value. A will equal 1/2. And when the numerical value of a changes, that means we're going to get a vertical stretch, again by a factor of the absolute value of a. Remember that when a is negative, it doesn't affect the stretching. That causes a reflection. A negative a value are two different transformations, just like a negative b value. But in this case, we have an a value of 1/2, so that's going to cause a vertical stretch. By a factor of 1/2 about the x-axis. And so you can see it doesn't matter whether you say about the x-axis first, the stretch factor second, or vice versa. It doesn't matter. It means the same thing. So now all the y values will get multiplied by 1/2. You're vertically stretching. Vertical goes up and down. It's the y values that go up and down. You're going to take 1/2 of all the y values. So y value of 4, take 1/2 of that. That'll be a y value of 2. Again, the x-intercepts are invariant because the y values are 0 there. 0 times any stretch factor stays 0. This point here has a y value of 2. We'll take 1/2 of that and get 1. This point here, a y value of 4. We'll take 1/2 of that and get 2. So this gives us the points on our new graph. After a vertical stretch by a factor of 1/2. Again, our invariant points are the x-intercepts. Whenever a graph is stretched about the x-axis, the invariant points will be the x-intercepts. Same ones as the previous one, plus and minus 2, 0. Our domain did not change because our transformation was vertical, not horizontal. So our domain did not change. And in fact, in this case, let's do this using set notation because this is the other way we can express. So all values of x, that line means such that, and in this case, x goes from -6 to +6 inclusive. So x is greater than or equal to -6, less than or equal to +6. And you'll also have to state what number system x belongs to. X is an element of reals. You with us, Judah? Okay. So if you're going to use set notation, you got to have the right shape of brackets, and you also have to make sure that you include the number system for it to be full and complete. Again, interval notation is much simpler. But you may be tested on set notation at some point. So you need to be familiar with that as well. Our range did change because, again, it was a vertical transformation. So it's all values of y between 0 and 2. So y is greater than or equal to 0, less than or equal to 2. And again, y belongs to the set of reals. Our mapping notation. In this case, we're vertically stretching by a factor of 1/2. All the y values are multiplied by 1/2. Okay? So in the last examples, we didn't have an equation for the original graph. It was just f at x. In this example, we do have the equation for the original graph. It's f at x equals x squared, a quadratic function, which we know goes through -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. So there's our original graph. And now we want to do g at x, which is 4 times f at x. So again, where is that 4? It's in front of the f. That means that it is an a value. We have an a value of 4 here, which means we're going to have a vertical stretch by a factor of 4. And that stretch is about the x-axis. So all the y values will get multiplied by 4. So I don't have room to stretch this point here. Y is already 4, and 4 times that is 16. Don't have room for that. But I do have room to stretch this point where y is 1. The x value doesn't change. It's just the y values that are multiplied by 4. The 0, 0 is invariant because a y value of 0 times any stretch factor stays 0. And this point here where y is 1 is also multiplied by 4. So the graph got really skinny compared to the original. That is the net result of vertically stretching by a factor of 4. Okay, so we've done our graph, we've described the transformation, we have an invariant point at 0, 0. In this case, the domain and the range will not change. The graph will go left and right forever. So our domain, if we use interval notation, have to use rounded brackets because you cannot ever include infinity. And remember, you always go from smallest to greatest, so it's negative infinity on the left, positive infinity on the right. And the range would go from 0, which is included, so hence we use the square bracket, up to positive infinity, which again cannot be included, so you must use the rounded bracket there. So there's our domain and range. We want to do a mapping notation as well. We want to write the new equation. So our mapping notation, because we vertically stretch by a factor of 4, all the y values are multiplied by 4. And our new equation for g at x is 4 times f at x. And the reason it's 4 times f at x is because we have an a value of 4, and a is in front of the function. It's a coefficient of x. And it's different than b, because if it was a b value, then the bx would be in brackets. Whatever happens to the x happens to the bx. The x is squared, so the bx would be all squared. But that's not what we have here. We have an a value, and a is a coefficient of f at x. It's a coefficient of x squared. Okay? So for question B, we'll start with, again, y equals x squared, using the same points that we did on the last one. And now we are going to apply the transformation with an a value of 1/3, which means we're going to get a vertical stretch by a factor of 1/3. So we're going to have a vertical stretch about the x-axis by a factor of 1/3. So all the y values will now be 1/3 what they were before. A y value of 4 times 1/3 would be 4/3, or 1 1/3. Notice that the x value doesn't change, only the y values. This y value here is 1, and 1/3 of that would be 1/3. A y value of 0 times any stretch factor stays 0. 1/3 of 1 and 1/3 of 4, again, is 4/3, or 1 1/3. So there's our new points. So this graph got wider compared to the original. That is the net result of vertically stretching by a factor of 1/3. It changed the shape of the graph. Didn't change the orientation, still opens up. Didn't change the position, didn't go left, right, up, down. Just changed the shape. Again, our invariant point is at 0, 0. And like the last one, our domain and range didn't change. Again, just for extra practice, let's do this one in set notation. And all we'd have to do here is say that x is an element of reals. That's basically saying all real numbers. X belongs to the set of all real numbers. It goes left and right forever. That's not true about the range, though. We could say all values of y such that y is greater than or equal to 0. And again, y is an element of the real numbers. So our mapping notation, again, all the y values are multiplied by 1/3, so x comma y maps into x comma 1/3 y. And our new equation, once again, we have an a value of 1/3. A is in front of the x. It's a coefficient. It's separate from the x. So that would be the new equation. Okay? So now we're going to do some practice with the b parameter, because b is in front of x, not in front of the function, not in front of the f, but in front of the x. So these two examples introduce the b value. And you have to remember that that causes a horizontal stretch, but the other part that's important is remembering that the horizontal stretch factor is the reciprocal of the b value. So a b value of 2 means a horizontal stretch by a half. We're going to have a horizontal stretch about the y-axis by a factor of a half. So now all the x values will change. You're going to take half of all the x values. An x value of -4, half of -4 is -2. The x-intercept is going to change because you're going to take half of -2, which is -1. It's the y-intercept that will be invariant because the x value there is 0. That's the point 0, 2. So when you multiply 0 times a half, it stays 0. Half of 2 is 1. Half of 4 is 2. So here's our new graph. After a horizontal stretch about the y-axis by a factor of a half. So we've got our new graph. We've described the transformation. We have one invariant point. That's the point 0, 2. And then all we have left to do are domain and range and mapping notation. So in this case, our domain did change because we horizontally stretched. We're going from -2 to +2 on the x-axis. So if I use integral notation, square brackets because those values are included. Also smallest number on the left, largest number on the right. Our range did not change. Both graphs have a minimum value of 0 and a maximum value of 4. And so finally our mapping notation, because we horizontally stretched by a factor of a half, all the x values were multiplied by a half. The y value stayed the same. Okay, so for question B, we have a b value of a half. And so that causes a horizontal stretch, but we need to remember that the stretch factor is the reciprocal of b. And the reciprocal of 1/2 is 2. We're going to have a horizontal stretch by a factor of 2. And again, the horizontal stretch is about the y-axis So now all the x values will be multiplied by 2. We can kind of guess where the first point will be. Here we have an x value of -4 times 2 would be -8, so approximately there. X value of -2 times 2 is -4. Again, the y-intercept is invariant. It's being stretched about the y-axis. The x value there is 0. 0 times any stretch factor stays 0. 2 times 2 is 4, and 4 times 2 again is 8, so we'll kind of guess where that will be. All right, so these graphs have a definite starting point and ending point. We don't have arrows on the end. And there's our new graph. Our domain, if we use set notation, it'll be all values of x between -8 and +8. And again, x is an element of real numbers. The range did not change. All values of y between 0 and 4. So that's set notation. Our mapping notation, we multiplied all the x values by 2. So x maps into 2x, but the y values stayed the same. And like we did earlier, we can do the same thing with an equation like f at x equals x squared. So we'll start by drawing x squared for both of these graphs. Might as well do them both. So for this first one, our b value is +3. And so we got to remember that that causes a horizontal stretch, and the stretch factor is the reciprocal of b. So we'll have a horizontal stretch about the y-axis by a factor of 1/3, the reciprocal of b. So all the x values will be multiplied by 1/3. So here, this point is where x was -2. Multiply that by 1/3, it'll be -2/3. Here we had an x value of -1 times 1/3 would be -1/3. 0 times anything stays 0. 1 times 1/3 is 1/3. 2 times 1/3 is 2/3. So this graph got super skinny. That is the end result when we horizontally stretch it by a factor of 1/3. So we've graphed it, we've described it. Our invariant point here is the point 0, 0. horizontally stretching at about the y-axis, so the y-intercept is invariant. And in this case, it just so happens that it's also the x-intercept. But the key is that it's the y-intercept that doesn't change. Our domain hasn't changed. It goes from negative infinity to positive infinity, and we must use rounded brackets when working with infinity. Range didn't change. It goes from 0, which is included, up to positive infinity, which is not. So we also want to do our mapping notation as well, the new equation. So because we horizontally stretch by a third, all the x values are multiplied by a third. And now with the equation, right, we have a b value of 3. That means you're going to replace x with 3x. And whatever happens to the x also happens to the 3x, in this case, squared. So when you square the 3 as well as the x, you'll get 9x squared. There's the new equation. And you can do either or in your calculator if you're checking. Put 3x in brackets and square it, or the 9x squared. It'll give you the same graph. Okay. So for question B, our B value is 1/4, which means we're going to have a horizontal stretch. But once again, the horizontal stretch factor is the reciprocal of B. So we'll have a horizontal stretch by a factor of 4. Horizontal stretch about the y-axis by a factor of 4. Our invariant point is the point 0, 0. It's the y-intercept, which in this case happens to be the x-intercept as well. But because we're stretching about the y-axis, the y-intercept is the part that's really invariant. Domain and range are the same. I'll just stick with set notation. So because we horizontally stretch by a factor of 4, the x values are multiplied by 4, which I guess I haven't done yet, so we'll go back and do that. Multiply all the x values by 4. So an x value of -2 times 4 is -8. -1 times 4 is -4. 0 times 4 stays 0. 1 times 4 and 2 times 4. Okay. There's our new graph. And for our equation, again, we're going to replace x with 1/4 x. So notice when you're putting it in the equation, you're using the b value. You're not using the stretch factor because those two are different numbers. The stretch factor is the reciprocal of b. But when you use the equation, it is the b value of 1/4. And again, whatever happens to the x happens to the bx. In this case, it's squared. So this would be 1/16 x squared. Right, and you can use the graphing calculator to check to make sure your graph is correct. We start with x squared as our first equation, and then if I just put in our b value and the x all squared, so b is 1/4 or 0.25. x, and I close the brackets and square it. And I can also use the 1/16 just as a check to make sure I did that part correct. I would just put the 1/16 in brackets as a coefficient in front of the x squared. So it's going to happen quick here. It's going to draw y equals x squared, then it'll draw the next two, and hopefully the third graph is drawn directly over the second. Zoom 6 to set our windows to their standard settings. Happen fast, but... And now you can use this and check against what you drew. Like we have this graph going through the point -4, 1. So let's check that by going into the trace mode and letting x equal -4, y. Oh, I'm sorry, I'm on the first equation, not the second one. There we go. Let x equal -4 and y equals 1. The other point I have on here is -8, 4. So if I let x equal -8, y does equal 4. So that matches what we drew. And we can do the same thing to the 2 points on the other side. Okay? So sometimes you're going to be asked to write the equation of a transform function. So some might look at this and say, well, how do you know? What is it being stretched about? It hasn't been reflected, but what is it being stretched about? And remember, the key is where are the invariant points? In this case, the invariant points are the x-intercepts, which means it was stretched about the x-axis, which means it was a vertical stretch. Vertical stretches are stretched about the x-axis. And again, because the x-intercepts are invariant, that tells us that is the line that is being stretched about the x-axis. So it's been vertically stretched, and to find out what that stretch factor is, we can compare the cusp points. So there's the cusp of g at x. Down here is the cusp of f at x. Sorry, I said that backwards. The top one is f, the bottom one is g. We're going from f to g. So here you have a y value of -2. It becomes a y value of -4. That means it's been vertically stretched by a factor of 2. A vertical stretch about the x-axis by a factor of 2. And we can take some other points to check those as well. For example, if we take this point here on f with a y value of 2, if you vertically stretch that by a factor of 2, you'll get a y value of 4, and there it is up there. Okay, so you can check with some other points to make sure you have the correct stretch factor, as well as the correct line that it's been stretched about. In this case, it's the x-axis. So if it's been vertically stretched by a factor of 2, that means our a value is 2. And therefore, g at x is twice f at x. An a value of 2 means that you have a coefficient in front of the function of 2. It's in front of the f. And if we're going to write a mapping notation for this, again, it was a vertical stretch by 2, so all the y values were multiplied by 2. Now for the second graphs, to go from f to g, note that the x-intercepts are different. It's the y-intercept that's invariant. That means it was stretched about the y-axis, which means it's a horizontal stretch about the y-axis. And we can go from one x-intercept of 2 to another x-intercept of 6. The second one is 3 times the first. So this has been horizontally stretched by a factor of 3. Same thing would work on the other side. An x-intercept of -2 to an x-intercept of -6. -2 times 3 gives us our -6. So in this case here, we have a horizontal stretch. about the y-axis by a factor of 3. Excuse me. Which means that our b value is 1/3. The b value and the horizontal stretch factors are always reciprocals of each other. And when we write our equation, it's the b value you put in the equation, not the stretch factor, right? When we write our equations with transformations, it's f at x or y equals a times f at b bracket x minus h. It's the b value that goes in the equation. So g at x will be f at 1/3 x. X is replaced with 1/3 x. Our b value is in front of the x. Whatever happens to the x happens to the bx. In this case, it's in brackets after the f. And because we horizontally stretched by a factor of 3, all the x values were multiplied by 3. So our mapping notation would look like this. Okay? So in this case, our original function is f at x equals x squared. We want to go to g at x. And because the invariant point is both the x and the y-intercept, we can actually write it two different ways. One of them being with a vertical stretch, the other being a horizontal stretch. Okay? So there's a couple different ways we can do this. One of them is just comparing points. So I think the easiest way to do this is to say, what if there was a horizontal stretch? So that would mean that we're going to multiply the x values by some value. So if we took this point right here and compare it to that point right there, because I know exactly what the x values are, I can do that. I'm going from an x value of 2 to an x value of 1. 1 is half of 2. If we're saying it's a horizontal stretch, it would be a horizontal stretch by a factor of 1/2. So I'll write number 1 here because this is going to be the first way we're going to do it if there is a horizontal stretch. If there's a horizontal stretch by half about the y-axis, that would mean that our b value is positive 2. And our equation for g would be 2x all squared, or 4x squared. So that is if we were horizontally stretching it by a factor of 1/2. So our mapping notation then, if we're doing a horizontal stretch by a factor of 1/2, all the x values are multiplied by 1/2. That's what the mapping notation would look like. Now the other way to do this, like I said, would be, let's say if there was a vertical stretch instead. And you could definitely do it by comparing 2 points. For example, I could take this point here on the original graph where x is 2, we have a y value of 4, compare it to that point there with the same x value. Now the y value is 16. So to go from 4 to 16, it would be a vertical stretch by 4. So the a value would be 4, which is exactly what we got when we simplified our equation. So you can do these by logic, which is what we have been doing all along, comparing 2 points. But there's another way you can do this. You can do this algebraically. So I'll show you how we could get an a value of 4 algebraically. So we're starting with f at x equals x squared. If we're saying that this can be done by a vertical stretch, again, that's an a value. So let's put a into the equation, ax squared. That is a general equation for any graph that's been vertically stretched from x squared. Now, to get our a value of 4, we can do it by subbing in a point on the new graph. We can use the point 2, 16. If this graph goes through the point 2, 16, that point must satisfy the equation. So we can let x equal 2 and y equals 16 in the equation and solve for a. 2 squared on the right is 4. Divide both sides by 4, and you'll get an a value of 4. That'll give us g at x equaling 4x squared. And you could have done the same thing to get the b value. To get the b value of 2, you could have done exactly the same thing. All you would have had to have done, and I'll do it below here. That's where I have room. If we say that g at x equals bx all squared. So again, if we're going to say that there was a b value, we got the b value to be 2 by using logic the first time around. You can do it algebraically as well. By again using a point on the graph, we can use the point 2, 16. So that's an x value of 2. So it would be 2 times b all squared. Take the square root of both sides, and you'll get 4 equals 2b. Then divide both sides by 2, and you get your b value of 2 that way as well. So we did it the first time around by using some logic, by comparing 2 points to get the horizontal stretch factor, and then we got our b value from that. But you can also do it algebraically to determine both a and b. Okay? Now for question B, you're starting with f at x and you're going to g at x. The shape of the graph didn't change. The location of it didn't change. What changed is that the direction of opening changed, or the orientation, right? The original graph is going upwards, the new one is going downwards. That means it was reflected over the x-axis. There's no stretch factor here because the shape hasn't changed. It's just a simple reflection about the x-axis. So g at x would equal negative f at x, or negative the absolute value of x. Because when you get a reflection about the x-axis, maybe you should write it here, a will be less than 0. A will be negative. Okay? So next example says write the mapping notation from y equals f at x for each of the following. So for that first one, we have an a value of 2. So you have to remember that causes a vertical stretch about the x-axis by a factor of 2. All the y values will be multiplied by 2 because it's a vertical stretch. Vertical goes up and down. It's the y values that go up and down, so those are the ones that are being affected. For question B, you have an a value of negative 3. So that's going to cause 2 different transformations. It's going to vertically stretch by a factor of 3 and also reflect it over the x-axis. Those can be done simultaneously by multiplying the y values by negative 3. That will vertically stretch it and reflect it over the x-axis. For question C, we have a b value of 4. So you have to remember that's going to cause a horizontal stretch. But their stretch factor is the reciprocal of b, so it's a horizontal stretch by a quarter. All the x values will be multiplied by 1/4. So I said yesterday, probably wouldn't be a bad idea to start a cheat sheet. Not one you can use on quizzes and exams, but one that you can always refer back to help refresh your memory, to make sure that you get all these details correct. Question D has an a value of 1/2 as well a b value of 6. So the a value of 1/2 means that it's vertically stretched by a factor of a. So all the y values will be multiplied by a, which in this case is 1/2. Because you have a b value of 6, that's a horizontal stretch, but the stretch factor is the reciprocal of b. So all the x values will be multiplied by 1/6, the reciprocal of b. Question E, you have an a value of -2, a b value of 2/3. An a value of -2 says all the y values are multiplied by -2 because it's been vertically stretched by 2 and reflected over the x-axis. But a b value of 2/3 means it's horizontally stretched, and the stretch factor is the reciprocal of 2/3, which would be 3/2. So all the x values will be multiplied by 3/2. The y values are multiplied by -2. Question F. We have an a value of -4, a b value of -1/3. So a b value of -1/3 means you're going to multiply the x values by -3. It's reflected over the y-axis. That's what the negative part does. The horizontal stretch factor is the reciprocal of b. So again, all the x values we multiply by -3 and all the y values by -4. Now we'll stretch it vertically by 4 as well, reflected over the x-axis. For this next one, I would get the y by itself by dividing both sides by 5 or multiplying both sides by 1/5. So this means we have an a value of 1/5, a b value of -4. It's our b value that will change the x components. You're going to multiply by -1/4. Right? The negative part will reflect it over the y-axis. The stretch factor is the reciprocal of b. So all the x values will get multiplied by -1/4. The y values will get multiplied by +1/5. It's been vertically stretched by a factor of 1/5. Question H, to get y by itself, I would divide both sides by -3/4. Dividing by a fraction is the same as multiplying by its reciprocal. So we can get the same net effect by multiplying both sides by -4/3. Dividing by a fraction is the same as multiplying by its reciprocal. So here we have an a value of -4/3, a b value of -1/5. It's the b value that's going to change the x values, and remember that the horizontal stretch factor is the reciprocal of b. So not only are all the x values going to be multiplied by -1 to reflect it, but they're also going to be multiplied by a 5, the reciprocal of 1/5. So the x values are multiplied by -5, the y values multiplied by -4/3. All the y values always get multiplied by whatever the a value is. It's the b value that you have to take the reciprocal of to get the horizontal stretch factor. Question I would get the y by itself by adding 3 to both sides. So, the pieces that will affect the x are what's inside the big square bracket. A b value of a half means a horizontal stretch by a factor of 2. And then you've also got inside the rounded brackets x minus 2, which means an h value of positive 2. Remember, the value of h is always the opposite of what it appears to be, which means it's going to shift 2 to the right, or you're going to add 2 onto the x values after you multiply by 2. You always do your stretching and reflecting first, right? And that just follows order of operations. You multiply before you add and subtract. And the parameters that affect the y numbers are the a and the k. We have an a value of 2, which means you're going to vertically stretch by a factor of 2 or multiply the y values by 2, and then add 3 on because a k value is plus 3, shifts it up 3 units. Try J on your own and we'll check it. So I would subtract the 5 from both sides first. Make sure we get the correct k value. Again, it's those inside parameters, b and h, that affect x. We have a b value of negative 2/3, which means it's going to be reflected over the y-axis, or you multiply all the x values by negative 1. But then you're also going to stretch it horizontally, and the stretch factor is the reciprocal of b. Our stretch factor will be 3/2, the reciprocal of 2/3. So the x values are going to be multiplied by negative 3/2, and then inside the rounded brackets we have x plus 4. So that gives us an h value of negative 4. Always the opposite of what it appears to be, which means the graph's going to shift 4 to the left, or you're going to subtract 4 from the x values. It's the outside parameters a and k that affect our y values. They're going to be multiplied by negative 1/2 and then decreased by 5. So there's the new mapping notation. Okay? So on the next page is a summary of everything that we've looked at so far. And then starting on page number 34, there is an assessment that you can work on. I will post the solutions to Google Classroom so you can check your work. Again, I can't stress how important it is that you actually do these assignments, check them on Google Classroom, make sure you're doing everything correctly. Practice is what makes you good at this stuff. Just repetition, the same thing over and over and over again, easier to remember. So do the practice, check it on Google Classroom, Make sure you're doing everything correctly. Okay?